Hi, this is our presentation of our undesigned lab to measure the friction between materials. The objective of our design was to measure the coefficients of static and kinetic friction. For some of the background and theory, we took a look at kinematic equations and derived a result that would allow us to figure out the formula of static friction based on the angle of the ramp that was found once the blocks began to move. Similarly, for coefficient kinetic friction, we figured out a formula that would let us derive the result based on a known acceleration and a known angle of the ramp. We came up with a list and a table of all of our equipment used and the total cost needed as a result, and differentiate between things that were already available and other sensors that we'd have to specially order from Adafruit.
Our sensors were selected for cost effectiveness and ease of access and use in order to quickly put together our equipment. So for these sensors, for the angle, the potentiometer was used to measure that. To determine the exact time the block begins to slide to help calculate acceleration, a beam brake was used. And an ultrasonic was also used to measure the distance, again, to contribute to our acceleration calculation. Three sensors from Adafruit were then found as they were cheap and easy to access, as all of these were available in the lab. Again, they might not have been the most precise, but we didn't exactly need precise for our application. For our setup, it was very simple. We just had a beam, a block of our material, and 3D printed mounting brackets for our sensors. This was all mounted on a swiveling hinge, which was our potentiometer to measure the angle. This is all mounted on a breadboard and connected to an Arduino to collect our data. We had two separate material beams. We only used one for our demonstration, but as can be seen here, we had one that was aluminum, and this is a lot more neatly wired here. For the design of experiments, as we had two different materials and two different mounting equipment that we could change, we had a two-factor, two-level experiment to do here. Those being the factors being a sliding surface and a block, and the high factor being wood and the low factor being aluminum.
So for the procedure, we simply placed the block directly before the beam brake, and then started the script on the connected PC to begin collecting said data. We would then manually, by hand, slowly lift the beam until the block begins to slide. After the block had reached the end, we would stop the script and copy the data over from the beginning of the beam brake until the ultrasonic distance sensor quit. Here's a video of it in action.
After moving and gathering the data from the block sliding down the ramp, we were able to collect it and put it in an Excel file where then we were able to interpolate it. Starting from the beginning, as you can see at a time of 0, we had a potentiometer voltage of 0.64 volts, which actually translated to a potentiometer angle starting at approximately 58 degrees of rotation. Using that angle, we were able to calibrate it to an angle of 0 to be then used and extracted further down in our data process. At the end, whenever the block reached the ramp, you could see where it is highlighted with a yellow circle around it. The beam brake sensor sent us a signal saying when it was broken and unbroken. At the time when the block slid past and it said unbroken, we can see that our angle was approximately 39 to 40 degrees, and that will be used to determine our coefficient of static friction. It also can be noted in these results that after the sensor was broken, the time stamp from 7.60 seconds to 8.10 seconds showed us the time and the distance traveled to be able to calculate our acceleration. Our acceleration results were then plotted in a distance per time graph, where the distance per time graph actually turned out to be a almost perfect parabolic curve, which is something we were looking for in the end. And with the equation plotted within it, we could take the second time derivative and get our acceleration. The acceleration turned out to be approximately 46.43 centimeters per second squared, and the angle it began to slide at was approximately 39.85 degrees. After using the governing equations from the first and second slides, we were able to get a coefficient of static friction of 0.34 and a coefficient of kinetic friction of 0.773. Our measured coefficient friction values and kinetic friction for wood on wood was a lot higher than accepted values. As you can see, these accepted values were taken directly from online, where you can search different materials and their varying static friction coefficients and kinetic friction coefficients. The accepted values are between 0.25 and 0.5 for static friction and 0.2 for kinetic friction, respectively. A lot of this error could probably be attributed to the fact that we milled out grooves onto our wood to hold the block in place so that it could slide down without moving off of the wood. But in reality, it probably took away from the natural features of wood sliding on wood, since there is surface roughness because we did not sand it after the milling process was completed. We also can attribute some of the error to our ultrasonic sensor not being as accurate as we thought. It only measured to approximately the 0.1 the tenths decimal for our distance, and would not go anywhere further to increase our accuracy. So this may also have had some impact on our results as well. Otherwise, repeating this experiment, if we could fix those two and possibly not use just our hand and maybe a crank system to increase the ramp for our design, we possibly could reach a coefficient of friction more accurate to the accepted values out there.